Hi, my name's Peter Bello and I'm an applications engineer with Arrow Electronics.
And I'm Robin Getz, Engineering Director of Analog Devices Systems Development Group.
We're here to tell you about the new Arrow High-Speed Data Acquisition Kit, which allows the designer to rapidly develop and prototype solutions while taking advantage of the high-speed and space-saving JSD204B interface. The kit is composed of two products: ADI's DAC2 Data Acquisition Board and Intel's Aria 10 FPGA Development Kit, along with the firmware and HDL required to make these work together. It incorporates the JSD204B Subclass 1 serial interface, which replaces the traditional LVDS and CMOS parallel interfaces with a more compact and scalable solution, while at the same time making provision for deterministic latency. In this demonstration, we are moving data between the two boards at a rate of 40 gigabits per second across 4 lanes in each direction.
The DAC2 board from Analog Devices features the 9680 analog to digital converter, a dual-channel 14-bit 1 gigasample per second ADC with a JSD204B Subclass 1 interface. The DAC2 also includes the AD9144 digital to analog converter, a 4-channel 16-bit 2.8 gigasample per second DAC, also featuring a JSD204B Subclass 1 interface. Clocking for the entire solution comes from ADI's AD9523-1 clock generator. With speeds up to 1 GHz, very low jitter, and 14 outputs, on-chip EEPROM, it provides a high-performance clocking, and it can be used to generate the sysref signals which the JSD204B Subclass 1 interface requires.
The Intel development board features an Aria 10 GX FPGA with an embedded Nios 2 processor running Linux. Built on a 20 nanometer process, the Aria 10 GX contains floating point DSP blocks operating at speeds up to 1500 gigaflops and can transport data at a rate equal to the JSD204B standard's maximum value of 12.5 gigabits per second per lane. This demonstration uses two additional components: the IIO oscilloscope application from Analog Devices, which we will use to configure the inputs and probe the outputs, and a PC to run it on. Here is the complete setup. The PC is connected to the Aria 10 board using an Ethernet cable. The two boards are connected together using their FMC connectors. 2 RF cables feed the signals from the DACs back to the ADCs, and the Aria 10 has its own power supply. We begin by using IIO oscilloscope to instruct the Aria 10 to generate 2 40 MHz sine waves. We then open up a plot window to view the waveforms in the time domain and hit the Run icon to start the demonstration. Before viewing the results, let's take a look at the path the signal takes as it travels across the two boards and back. Using IIO oscilloscope, we instruct the Aria 10 to generate 2 sine waves within its direct digital synthesis block. The two signals are at the same frequency, but 90 degrees out of phase with each other and represent the in-phase or I and quadrature or Q signals. The Aria 10 formats and serializes the data according to the JSD204B standard, then sends it out along 4 serial lanes across an FMC connector to the DAC2 board.
On the DAC2, the JSD data is routed to the AD9144 DAC, where the digital data is deserialized and converted to analog. The resulting analog signals are then sent out through SMA connectors. In this example, we have them attached to a pair of RF cables. These cables are then looped back to the DAC board into SMA connectors feeding the analog inputs of the AD9680 analog to digital converter. The 9680 converts the analog signals to digital, formats the serial to the JSD204B standard, and then sends it along the serial lanes across the FMC connectors to the Aria 10 FPGA. The Aria 10 then converts the high-speed bit stream back into a parallel format, captures the data with the JSD204 interface framework, which includes HDL and drivers for the ADC, DAC, clock, and FPGA IP to configure everything and see the resulting waveforms on the IIO oscilloscope.
Let's view the results. Here we see 2 sine waves after they have traveled from the Aria 10 to the DAC2 and back, spaced 90 degrees apart as expected. Now we will look at these in the frequency domain. For this test, the IIO oscilloscope tool takes the measured data received by the Aria 10, runs a fast Fourier transform on it, and displays the results, much like a spectrum analyzer. By right-clicking in the plot window, we can identify the frequencies of the resulting peaks. Looking at the box on the lower left of the plot window, we see that there is a peak for the DC component and one for the fundamental at 40 MHz, along with harmonics or multiples of the input frequency. We also see the images or negative frequency peaks which result from performing a Fourier transform on the two frequencies together.
We can also intercept the signal halfway between the DAC and the ADC when it's in the analog domain and check its integrity. To do this, all that's needed is an oscilloscope with sufficient bandwidth. Here, we've connected the outputs of the AD9144 DAC directly to the scope. Looking at the screen, we see two sine waves, each at a frequency of 40 MHz, which agrees with our initial programming. The ADI JESD204 interface framework helps people easily bring up their JESD204 systems and allows the system to be as dynamic as possible. Runtime configuration changes are possible, and we can see I can quickly change the ADC sample rate, which requires reconfiguration of all the clocks, the ADC itself, and the FPGA IP, which the framework understands how to do.
As we have demonstrated, the Arrow High-Speed Data Acquisition Kit is a highly effective tool for developing, prototyping, and speeding the time to market of your high-speed JESD204B products. For more information or to order this kit, go to arrow.com or contact your local Arrow sales representative. For those who may want to investigate other FPGA devices like the ARIA 10 SoC, this same DAC2 board will work, and example designs are available. Please contact your local Arrow FAE for more information.
On behalf of Arrow Electronics and Analog Devices,
Thank you for watching.